Alright, in this lab, there's a video of a cardboard box being dropped from about shoulder height. In this lab, we will extract motion data and construct models using Newton's second law and compare the models to the observations. So, this video was recorded at 30 frames per second, and it was dropped at the student's height of about 1.778 meters, and was used to calibrate the length scale. The coordinate system was chosen with the origin at the center of the box just before it was dropped, and the y-axis was aligned so that the object moves along the negative y-axis. The axis was tilted because the camera was tilted when the motion was captured. From analysis, we obtained the motion of the object as a function of time, shown as the blue circles, and the motion of the fallen object lasts about 0.533 seconds. The object begins at the origin, where t equals 0, and the position vector is 0, 0, 0 meters, and 0 velocity. Using Newton's second law, since the velocity is changing, delta v is not equal to 0, and therefore F net is also non-zero. So there is at least one force acting on the box. Earth exerts a force, the weight force, where W equals negative mg delta, hat J. Since this is the only force acting on the object, the weight of the force is equal to the object. Alright, so we gave the ball the mass of 0.02 kilograms, the position vector is the 0 vector, and the ball's velocity is 0, negative 1, 0. We gave delta t a very small value, so 0.001, and g the value of 9.8. J hat is also the vector 0, 1, and 0. And then we gave the value, the equation for weight, which is negative ball dot m times g times j hat. So when we compare our graphs, see the model is the smooth blue line, and the observation is the orange circles. And there is a space between because that is of other forces acting on the box. We can fix this by actually adding in air friction to this, and the equation we have is the negative b times ball dot velocity. And we added that into our F net equation. And the way we found what B is by plugging in different values of B and finding what gives us the best position, which is equivalent to the ending position of the observation. We can then create arrows that represent the vector forces, and we need to decide where to draw the tails of the arrows. We are using ball.pos to place the tail of the fallen object, but we still need to decide how long and what directions to draw the arrows, and we need to make them proportional to their force. So for the weight, the value is approximately 0.196 newtons, and then we divide the mass of the box by the weight of the box, and that gives us the arrow scale, which is 10.2. We then multiply that also by the other arrow, and we'll find the value of friction and velocity. As you can see here, the blue arrow grows as time progresses, and the yellow one remains the same. But when we look at the graphs, as you can see with these graphs, the model that accommodates drag is a lot closer to our observation.